Hi, I'm Albert Lin. I'm an undergraduate at Princeton University, and I worked in Professor Somil Bansal's lab at the University of Southern California last summer. In this video, I will introduce our framework for generating formal safety assurances for high-dimensional reachability. As more autonomous systems are deployed into the real world, formally guaranteeing the safety and performance of these systems becomes increasingly important. Hamilton-Jacobi reachability analysis is a popular formal tool for providing such guarantees by computing a system's backward reachable tube, BRT, which is the set of all states for which, for all possible control actions, the system state will reach a given target set at some time within a given time horizon. We can obtain the BRT by computing the value function of a corresponding optimal control problem. Along with the BRT, we can obtain a safety controller to keep the system outside the BRT. Unfortunately, numerical grid-based reachability methods suffer from the curse of dimensionality and are intractable for general high-dimensional systems. A recently proposed method called DeepReach leverages a sinusoidal neural PDE solver for high-dimensional reachability problems, whose computational requirements scale with the complexity of the underlying reachable tube rather than the state dimension. However, neural networks can make errors, so there are no formal guarantees on the DeepReach solution. Our main contribution is a method to compute an error bound for the DeepReach solution by using a self-consistency property of the learned value function and its induced optimal controller. This error bound can then be used for reachable tube correction, resulting in a safe approximation of the true reachable tube. Computing this error bound is a challenging optimization problem in general. We propose a scenario-based optimization approach to compute a probabilistic bound on this error correction for general nonlinear dynamical systems and demonstrate the efficacy of the proposed approach in obtaining probabilistically safe reachable tubes for high-dimensional collision avoidance and rocket landing problems. Consider a 9-dimensional multi-vehicle collision avoidance system involving 3 independent Dubin's aircraft. We want to guarantee that we can avoid any collision of aircraft in this system, so the target set is the set of all states where there is a collision of aircraft. Then, the BRT is the set of all states where a future collision is unavoidable within the time horizon despite our best control efforts. In this case, the BRT represents a set of unsafe states, and remaining outside of the BRT guarantees safety. 3 slices of the BRT learned by DeepReach for the collision avoidance system are plotted in orange. Since the DeepReach solution may have errors, we do not yet have a formal notion of safety. To obtain a probabilistically safe approximation of the true BRT, our key idea is to compute a uniform correction bound for the learned value function. Essentially, if a particular state is outside the learned BRT, then starting from this state, the learned value function's induced safety controller should keep the system trajectory outside of the target set at all times. Otherwise, we cannot ensure the safety of this state, and the value function should be corrected such that this stays inside the BRT. Once all such states have been encompassed by the modified BRT, we have obtained a provably safe approximation of the true BRT. Computing this uniform correction bound can be posed as an optimization problem. In general, it is challenging to tractably compute this metric, since the learned value function can be nonlinear and hard to optimize. We propose to compute a high confidence bound on the metric by utilizing a random sampling procedure referred to as scenario optimization. Our verification algorithm iteratively obtains tighter approximations of the metric until convergence. If our verification algorithm converges, then we can recover a new safe set defined by our estimation of the uniform correction bound. Importantly, we can make formal probabilistic safety guarantees for the recovered safe set. Here are the results of using our method to recover probabilistically safe BRTs for the 9-dimensional multi-vehicle collision avoidance system. This histogram shows the frequency of the minimum pairwise distance between aircraft along trajectories which spawn from states sampled within the learned safe set and the recovered safe set. The collision distance is indicated by the dotted line. Note that prior to verification, the learned safe set contains unsafe states. The recovered safe set shows no such violations of safety. Here is the learned and recovered BRT for a 6-dimensional rocket landing problem, where now we want to reach, not avoid, the target set. The system trajectories reach the target set shown in green from the states within the recovered safe set shown in blue. We can recover higher quality safe sets if instead of a uniform correction bound, we compute a more nuanced value function correction. For instance, we could bin the state space into separate subregions and independently verify each subregion, allowing a greater correction bound for subregions with high error and a smaller correction bound for subregions with low error. However, the efficacy of such an approach depends heavily on the selection of subregions, and so we defer this to future work. In conclusion, we have presented a framework for generating formal safety assurances for high-dimensional reachability. We utilize a scenario-based optimization algorithm to compute a probabilistic bound on the error of the learned value function and use this bound to recover a safe set with probabilistic guarantees. Although we have shown how to apply our method specifically to DeepReach solutions, we can use it with any general approximation of the value function and optimal controller. Please refer to the project website and paper for more details. Thank you for watching.